In this video, we're exploring the effects of climate change and nutrient input on the Baltic Sea ecosystem using our holistic Baltic Sea Atlantis ecosystem model. With climate change, it's predicted to increase in temperature. But besides this, it's also predicted to rain more because of changes in air temperature. Now, when it rains on land, nutrients are carried with to the river, as well as excess of fertilizers from agriculture and animal manure. This runoff of small particles is carried down the river and will eventually end up into the sea. So, more rain will affect the amount of nutrients, but it will also affect the salt concentration as more fresh water will enter the ecosystem. This is especially the case for the Baltic Sea because of its low salinity and little water exchange with the North Sea. So, climate change for the Baltic Sea is predicted to increase the water temperature, decrease the salinity, and increase the nutrient input load. But how much? That will depend on governmental regulations and the climate change path. The IPCC created several forecasts, one in which more effort is put into renewable energies. This one has a temperature increase of 1.5 degrees Celsius, a small decrease in salinity, and an increase in nutrient input. Another forecast uses more non-renewable energies and has a predicted increase of 2.7 degrees Celsius, a higher decrease of salinity, and a higher increase in nutrient input. However, we not only took the results from one global climate model, we took the results from 3 different climate models. Each of them had their own predictions, and by combining them, we had a range of temperatures, salinities, and nutrient loads within each scenario. This enabled us to incorporate some uncertainties from these different climate models. We will show the effects on cod, sprat, and herring, the main commercial fish species for the Baltic Sea. We investigated, for instance, how much their biomass changed, whether it increased or decreased for the different scenarios compared to our baseline. We created several scenarios according to the different pathways, RCP 4.5 or 1.5 degrees increase, and the RCP 8.5 or 2.7 degrees increase, together with different levels of riverine nutrient inputs. Each color is a scenario. The high nutrient input scenarios are colored green, with a dark and light green for the high and low climate scenarios. We also had nutrient inputs similar to today, with a high and low climate scenario shown by the yellow colors. And finally, the blue colors show the scenarios with a low nutrient input, lower than present day, for both climates and the present climate scenario. The model shows us that the high nutrient input, or green colors, results in a decrease in cod but an increase in sprat and herring, while a low nutrient, the blue colors, results in an increase in cod and a lower increase in herring. When comparing the climate scenarios, so the darker colors of RCP 8.5 versus the lighter colors RCP 4.5, we see that a larger climate change resulted in even less cod but more sprat and herring. The model also indicated that there is a larger effect due to the difference in the nutrient loads compared to the difference in climate strength. As is shown here, the difference between dark green and dark blue, high nutrient versus low nutrient, is larger than the difference between dark and light green, high and low climate increase. And finally, the uncertainty bars show the differences in results from the ensemble modeling using 3 global climate models. The model shows that this difference is for most cases larger than the difference between the high and low climate scenario, so the dark versus the light colors. However, these results only hold when the spawning can take place. Cod, for instance, need a specific temperature, salinity, and oxygen to have a successful spawning. When the values of these thresholds are too high or too low, spawning will be affected, and so the population. So, to sum up, we see that the differences in results caused by the nutrients are larger than due to the climate. We also see that the difference in result caused by the ensemble modeling is mostly larger than due to the climate. In general, we see that an increase in climate caused a decrease in cod and an increase in spread and herring. An increase in nutrients caused an even higher decrease in cod and a higher increase in spread and herring. The combined effects of nutrient and climate increase resulted in a larger decrease in cod and a larger increase in spread and herring. On the other hand, a decrease in nutrient despite the change in climate resulted in an increase for cod and herring. However, this is as long as the hydrographic threshold for spawning are not reached. If you want to know more about the research, you can go to the article, for which the reference is added in the credits.